Great. Um, Come to today's class. I hope you had a great time. You had a good Veterans Day. I hope we all had time to just spend the day with family and also to remember the nation's great people who laid down their lives to give us all the freedoms and the things we enjoy now. Great. So you're welcome to today's class. I hope we are excited to do chemistry as always. I know it's your favorite subject. I know you love chemistry, and I love chemistry too. So that makes us a pair and be a good team together, right? We work well together, right? Great. So we want to go straight into today's class. You want to follow through, please. Make sure you get your bell ringer done. If you've not done that, please do that now. Get your bell ringer. Everyone, let's go through our bell ringer. You can see it. Write your response for your bell ringer in your notebook. In your notebook right now. Yeah. So hopefully you've been able to get your bell ringer. Hopefully. So we're going to in a minute we're going to try and get the bell ringer together, all of us together. But I gave you some time. If you just still have not done this, try to do the bell ringer yourself. Think about it. We've done this before. We started talking about stoichiometry some weeks ago. We're going to go back to it, but this time we're going to tie in all we've been learning so far about balancing equations, redox reactions. We're going to tie all of them together. Great. So by now, I'm sure we've all gone through this. If you haven't, I'm here for you. We're going to go through it together. Okay. But I want to just encourage you, please, don't just listen to this and be happy and just listen to the video. Okay. I really encourage you, please, and please again, Stop everything you're doing, put your phones away, pay attention, get a notebook, write down as you're listening. Write down as you're listening. Okay, that's the best way to learn. The best way to learn is to write as you're listening, okay? And that will do you a lot of good. I'm going to try and turn down this. I don't know if you can hear there's a noise in the background. I'm going to try and turn it down. So just give me a minute. Okay. Great. So now I'm back. Great. So we're going to do the bell ringer together. I gave you enough time. Hopefully you did it. So let's go through this together. Let's go through this together. Let's go through this together. So the question was stoichiometry. Remember what this means? So I'm just trying to get you to remember what we started because you're going to need it in this lesson. So let's see. What did we say stoichiometry is? I gave you clues to help you out. Remember the word. Remember the word stoichion. Remember the word stoichion. Stoichion. Now we said the word stoichion and metry. At least if you can't remember anything, what do you think metry is? Metry. Think about all the things that had metry. Think about the word meter. What is a meter used for? A flow meter. An electric meter. What do you think it is for? Metron is from the Greek, which means measure. It means measure. Okay, so that means to find the quantity of something, right? To try and describe something in quantities. Maybe one thing in relation to another, right? So metron, keep that in mind. And we said stoichion is also a Greek word which stands for elements. Elements. Element, or the basic form of things, right? So we are looking at quantifying elements. Does that help you to remember what stoichiometry was all about? Remember we started talking about how much of let's say carbon is in this compound, or how much of oxygen is in this compound, or how do you find the number of moles of carbon in a certain compound, or how do you find the number of molecules? Remember where we started talking about the Avogadro's number? Who remembers Avogadro's number? We said Avogadro's number is 6.022 times 10 raised to the power minus 23. If you don't remember, if 6.023, if you don't remember, I know exactly what to do. Let's go back. We're going to go back as far back as when we were doing, just to make sure that you remember that we've done this before. And we did this together. You and I, in this class, we did this together. So we are going back just to help. I'm happy I have all my notes here. See, all my notes are always here. So we've done this before. Good. We are going back, 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 back. Good. So this is so good. We've gone so far back. We started talking about, yeah, exactly, composition. I want to show you just Avogadro's number, then we're gonna go back. If you look in your notes, you're gonna see that Avogadro's number is there. Remember, look at this formula. We're gonna need this formula again. So if you've forgotten, I'm just showing you, go back to your notes. N equals to mass over molar mass. We're gonna need that formula. See, remember I told you that in chemistry we're just combining everything we've learned. Good. So this is another formula we're going to need. We said number of atoms. Look, number of atoms or number of molecules is equal to Na. Now Na is Avogadro's number multiplied by the moles. To find the number of molecules, you just multiply the Avogadro's number by the number of moles. So what is the Avogadro's number? This is at 6.02 times 10 raised to the power 23. So I put negative there. It's not supposed to be negative. So Avogadro's number is 6.02 times 10 raised to the power 23. That's all. I wanted to make sure we remember Avogadro's number. Okay. So keep these two formulas. We're going to need these two formulas. This is the same formula. N equals to mass over molar mass. It's going to be very useful. The second formula you need to remember is the formula that has the Avogadro's number. Good. Number of atoms. Now, number of atoms, it can be the same as number of molecules. We're doing a review because you're going to need this. That's why I'm going back. We said number of molecules, number of atoms or number of molecules is equal to Na, which is Avogadro's number. This is Na. It's right here. Na is 6.022 times 10 raised to the power 23 per mole. That is the unit for Avogadro's number. So we're going to need these two formulas. So I'm transporting this back just to remind you there are two formulas we need to remember. We need to remember what Avogadro's number was. We need to remember the formula for molar masses. We're going to need these two formulas, okay? So let's take these two formulas. Now we're going back to where we are right now. I'm going back to our current lesson and we're going to transport all we're learning right now. Oh, great. So this is it. So let me correct myself. So Avogadro's number is 6.02. It's 6.02 and there's no negative. Good. So 6.02 times 10. This is Avogadro's number. It's represented by Na. So you need to remember Avogadro's number. You need to remember this formula too. We're going to need it in this lesson. The second formula you need to remember is equal to N equals to M over big M, where we said this is mole or this is amount of substance. Amount of substance is measured in mole, so it's the same thing. We said the amount of substance, which is N, is equal to the mass, which is in grams. So this is your mass. Oops, sorry. Your mass, which is in grams. I'm writing the unit in brackets. Your mass is in grams. Your amount of substance is in mole. Now this stands for molar mass. And molar mass is measured in grams per mole. Okay. So keep this. Keep this. Keep this. These two formulas. So we need to know Avogadro. And now the final formula which uses Avogadro's number, it says that number of whatever you're looking for. So if it's a number of atoms, you use a number of atoms. If it's number of molecules you're looking for is number of molecules. So number of atoms equals Na, which is Avogadro's number, multiplied by the mole. I'm reviewing because we're going to need these. Okay, we're going to need these formulas. Are you good? If you're not good, this is the chance. Write down these formulas again because we're going to use it. Today's topic is stoichiometry of reactions. So we are doing stoichiometry, but this time we are taking stoichiometry a step further. We're going to talk about stoichiometry in terms of reactions. Okay. So I'll give you a second, please. Write these formulas down. If you haven't already, write these formulas down because you're going to need it. Great, man. Now I'm expecting that you're done writing. So let's go. We want to start. So today we're going to look at reaction stoichiometry. What is reaction stoichiometry? Then we're going to look at moles of reactants required in a reaction. So we're trying to find the moles or the amount of the reactant. So whatever elements are in the reactant, we want to find the amount of how to find the amount required. So that means that you want to achieve a set, you want to create a certain product, right? But to create a certain product, you need certain reactants to combine, create a reaction so that you achieve that product you're looking for. Normally, every product comes with something called a byproduct. So let's say you cause a reaction, the reaction creates a product and a byproduct. So normally the byproduct might be a gas. So I want a certain gas to be released. But for a certain gas to be released, I create a reaction so that the product will come with a byproduct, which is a gas. Then I achieve my gas being released. Okay. We're going to see that this is used in how airbags are used. How many of you have ever thought about it? How does your airbag work? If you know what an airbag is a safety mechanism that is in your car. When your car gets into a head-on collision, certain bags pop up just to save your head from having a direct impact on any other object because it can cause a concussion to your head. So airbags operate with a certain phenomenon. We're going to learn more about that as we go through this. So I hope you're getting excited about today's class. I do, we do, you do. We're going to look at that. Now, number of product molecules generated by a reaction. We're going to look at that soon. So we're going to look at how to find the number of product molecules. So we want to know, we're going to look at how to find the moles of the reactant. And we're going to also look at how to find the number of product molecules generated by a reaction. Great. We're going to look at some I do, we do, you do. Then we're going to look at relating masses of reactants and products. Relating masses of reactants and products. Then we're going to look at some I do, you do, we do. Great, 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 great. Great. So I hope you're ready because I am. Great. So let's go. We're starting with reaction stoichiometry. So we have a background already. We started talking about stoichiometry. We know it has to do with quantifying elements, like the quantity, trying to find the quantity of elements. So we want to go further. Let's see. We're saying that in reaction stoichiometry, one of the first thing you want to think about, you want to think about balanced chemical equations. You see, so remember when we started chemistry from the beginning, I told you that in chemistry we're trying to communicate, but our mediums of communicating is in symbols. Okay, so that instead of me telling you a whole sentence, I can just put elements in symbols and the symbols communicate. Now, one of the ways we communicate in chemistry is using chemical equations. So instead of telling you a whole story or telling you a whole guideline for doing something, I'll just write one chemical equation. One chemical equation has so much information in there. So we're saying that in a reaction stoichiometry, we want to think about a balanced chemical equation as not just a normal equation. Anytime you see an equation, first of all, you want to make it balanced. Because as soon as you make it balanced, you have opened up a lot of information hidden in that balanced equation, and that's what we're going to look at. So we're saying that a balanced chemical equation gives you a lot of information. So anytime you see a balanced equation from today, don't think of just a bunch of symbols that you don't understand. Think of it as, okay, this is telling me something. What is this chemical equation telling me to do, or what is it trying to inform me about? Okay, great. That's number one. Number two, we're saying that In reaction stoichiometry, we are trying to analyze quantitative relationships. What does that mean? That's a big word. Quantitative, that's the first one, relationships. So we're trying to look at different elements and their quantities and how they relate with each other. So means that, let's say you have carbon, you also have oxygen in there, and you have maybe another element formed. We want to look at the quantities of the individual elements and how they related. So maybe you're going to pick one element and relate it to another element and compare their quantities, right? And that's what reaction stoichiometry is going to open us up to. Okay, so that's what we're going to look at, right? Great. So that's where we are at the moment. So I want you to think of a recipe. Think of a recipe. I remember when we were in class, Ariana said she likes to be in the kitchen a lot and she likes to cook. So let's imagine Ariana is cooking food, right? So Ariana is cooking. To cook, you need a recipe. A recipe is just trying to tell you the quantities you need to put together to achieve whatever meal you're trying to create, right? So that's a recipe. So think of any recipe you know. Any recipe you can think about, it's a good way to understand what is happening in a chemical reaction because in every recipe, you're mixing some components together to achieve or create a certain end result. That's what a recipe is. So let's look at this recipe together. So we all have here, let's look here. So there's a recipe here. This recipe has been tested and they know the end result. Based on the end result, they can backtrack or back calculate to know, okay, that if I have 1 cup of pancake mix, right, and I add it to 3/4 of a cup of milk, and I add 1 egg to it, it can make 8 pancakes. I don't know if you're seeing what is going on here. So we are combining different elements to achieve a result. The end result here is what 8 pancakes. The individual components put together is pancake mix, milk, and egg. So these three are the individual components. The end result is pancake. So we can think of this as the pancake mix, the milk. So we can think of it this way: the pancake mix, the milk, and the egg. These three can we can say these are the reactants. And what the product is what is the pancakes. But you see that to achieve a certain number of products, you need to put together a certain individual quantities of reactants. So then the numbers here is what we call in chemistry, we call them coefficients. When you're balancing equations, you put certain numbers. You remember when you're balancing equation, you put certain numbers in front of the elements. Those numbers are called coefficients, right? And so those coefficients is what we're seeing here. Remember, so those coefficients are giving us information about the proportion of each element in the achieved or the desired product. So look here, we want to make 8 pancakes and we needed 1 egg, we needed 3/4 cup of milk, and we needed 1 cup mix, 1 cup of pancake mix, right? And this gives us our desired result, 8 pancakes. Is this making sense, everyone? I hope this is making sense. If you love pancakes, I'm sure now you already know how to make. If you've never made a pancake before, I just showed you a good way. You can make a pancake. All you need to do is to get these 3 things, and you're good to go. You're ready to make a pancake. Great. So I hope we are all good so far. So far, you're good with what we just illustrated, right? Okay, if you're good so far, then that means we're making good progress. And we're going to try and now transfer what we just learned. Okay, so let's transfer what we just learned. So now, with what we just learned, we're going to transfer the knowledge. So, okay, we know that to make 8 pancakes, let me change the color. So I want to make 8 pancakes and I needed these. So this time, let's say I'm increasing, I don't want to make 8 pancakes. I want to make 24 pancakes. So look here. So this time I'm increasing the product. As soon as I increase the number of the products I want to achieve, it affects the proportion of each of the reactants. So how do we know the proportions that will be affected, and would they increase or decrease? First of all, what do you think? Do you think that if you increase the product you're trying to achieve, would that increase the number of reactants? Would that increase the proportions of the reactants, or would that decrease the proportion of the reactants? I want you to think about this. At first, you wanted to make 8 pancakes. You needed 1 cup of pancake mix, 3/4 cup of milk, and 1 egg. So this time you want to make 24 pancakes. Would that require an increase in the individual proportions of the reactant, or would that require a decrease? That's my question. What do you all think? I would think for a second and write what you think in your notebook. Write what you think in your notebook. Great. So let's see together what is going to happen. I want to make 24 pancakes. So to find so we want to make 24 pancakes. How we want to know how many eggs you're going to need if you want to make 24 pancakes. To do that, let's see what we're going to do. When you're making 8 pancakes, the ratio for eggs against pancakes was just, so we're going to, everybody look, pay attention to this reaction. I'm trying to show you how they came by the answer. In this reaction, comparing eggs with pancakes, you're going to have 1 egg, 1 egg. Today we are all cooking. 1 egg is to 8 pancakes. Can you see that? So 1 egg is to 8 pancakes. We call this just a ratio. This is just a ratio. You're going to see the technical term for this. So we have 1/8. 1 egg here, do you see that? Is to 8 pancakes. Okay, let's write another ratio. This time, let's write a ratio for pancake mix and the pancakes. You see that you're going to have something similar. 1 cup of pancake mix. 1 cup of pancake mix will be is to 8 pancakes. So you see the ratio is still what? 1/8. Then now the last ratio we want to develop is the ratio for the milk. So this was egg against pancake. The second one was pancake mix against pancake. The last one we're going to try and do cup of milk again. So let's do it. 3/4 cup milk, cup of milk divided by what? Divided by, so 3/4 is to what? Is to 8 pancakes. That's the ratio, right? Great. So now we have the ratio for all the three of that. I just wanted to make sure you see what is going on here. Now we can simplify 3/4 is to 8 into something else, but that's not the goal for today. I just wanted to be able to see how we get the ratios. Keep this in mind. So if you're looking here right now, to be able to be able to find to be able to find the number of eggs you needed for 24 pancakes, all you have to just multiply the 24 pancakes by the ratio of the egg to pancake. So this is it. Our ratio of eggs to pancake is here. It was 1/8. So all they did was that they just multiplied the 24, which was their desired number of product, by the ratio of the egg to pancakes from the original equation. This is it. So they just took 24 multiplied by 1/8. 8 goes here 1. 8 goes here 3. 3 times 1 gives you 3. So we know that 3 eggs will be needed if I want to make 24 pancakes. If I want to know how many pancake mix, it's going to be the same thing. 24 multiplied by 1/8. It's going to be 3. So it's going to be 3 eggs. It's going to be 3 pancake mix or 3 cup mix, however you want to write it. Okay, it's going to be the same thing. If I wanted to find for milk, so let's do milk. If I wanted to know the milk, it's going to be 24 multiplied by 3/4. So let me put this all in bracket. We have 3 divided by 4. 3/4 all divided by 8. So I want to put this in bracket so that we don't confuse ourselves. Now remember, let's solve what is in the bracket first. So we have 24 multiple. So all this is algebra, okay? Don't get confused. You're going to have 3/4 multiplied by 1/8. That's all you have here. Okay. And so this will give you what? We can simplify this further. So I'm going to clean so that I can make space, okay? So if you didn't have what I was doing, write it down because I'm about to clean some of the things I wrote. Or you can pause the video here, write down in your notes, then you continue because I'm about to clean some of the things I did ahead. So let me clean all of this so that I can make more space on this screen. Great. Oh, no. So I'm going to continue this here. I'm going to continue the work I was doing up here. So I'm continuing this up here. So please follow. Okay. You can pause at any time. You can go back at any time to realize what was happening. Oh no. Good. So we have 3/4. I'm going to continue this up here. So we're going to have, let me create this box here so that we all know what's happening. We're going to have 24 here. But now 24 is now multiplied by whatever is in this bracket. We have 3/4 multiplied by 1/8. There are a lot of ways to solve this. One of the ways is, let's create we're going to have 24. You can just do it straight out. I want to make it straight out. 24 now multiply by, we're going to have 3 8 times 4 is what? 32. So put 32 here. Now we can simplify these. I just wanted to simplify this into the simplest form for you. We're trying to find how many milk will be needed for 24 pancakes. That's what we're doing. So 8 can go into this one 3 times. 8 can go into this one 4 times. Do you see that? So we have now, then 3 times 3 gives you 9. So finally we're going to have 9/4. So this is how much milk you need to make 8 pancakes. If you want to write this in a mixed fraction, it's going to be one whole number. All this is algebra. I'm not an algebra teacher. I'm just giving you a recap because you're going to need your math in this topic. Okay, so you're going to have one whole number 5, 5/4. What that means is that we're going to need one whole cup of milk. Then, so let's do this together. 4/4 plus 5 gives you 9/4. So, however you want to interpret this, so this is in the mixed fraction form. That's one whole number 5/4 or 9/4. Okay. Oh, no, no, sorry. You can even make it easier. Let's do two whole numbers. So you're going to have, sorry, you can have it this way. Let me rewrite this. Instead of one whole number, you can make it two whole number. Cause so this is what it means. If I let's do two whole numbers, that makes it easier. So 9/4 in mixed fraction, you can have two whole number 1/4. So that 4 times 2 gives you 8. 8 plus 1 is 9. So 9/4 is the same as two whole number 1/4. What this means is that if I want to make 8 pancakes, I need to pour 2 cups of milk, then an extra 1/4 of the cup, and that'll give me 24 pancakes. That is what we just did. So you see, we just did some chemistry or some calculations in the kitchen right now. So now I know that if I want to make 24 pancakes, I know how to achieve that. Okay. Does this make sense? If this doesn't make sense, pause the video, go back, watch it one more time. Okay. All we did here is that we had to find the ratios of one element against the product we're trying to achieve. When you have that ratio, then now if you want to increase your product, just multiply your desired increased product by the ratio. And you know how much of that particular reactant you need to increase to get the desired product. That's what we just did. Okay. That's exactly what we just did. But we were using pancake mix and milk and egg to make a pancake. Now we're going to go further. So if you didn't get that, just pause, go back and make sure you get that. We're going to transfer all we just did, but this time we are not going to talk about pancakes. We're not going to talk about chemical elements. Okay, so are you ready for the chemical elements part of it? I hope you are because I'm ready to. So now we're going to think about exactly what we just said, but this time we're going to look at ammonia. So imagine this time you're making ammonia. Instead of making pancakes, you're making ammonia. So this is the recipe, if you want to call it a recipe. So this time our recipe, what you call recipe is the same as your chemical equation, your balanced chemical equation. Remember, you need to balance it first because you're balanced. Once you balance it, then you can know the right proportions that are needed. So from this chemical equation, we know that if I want to make two of ammonia, I told you anytime you don't see anything by the element, it means there's one here. So because there's nothing written here, it means there's one. That's a big one. So if I want to make ammonia, two of ammonia, I need one of nitrogen. If you don't know what N is nitrogen. You should know that by now. N is nitrogen. So if I want to make two of ammonia, I need one of nitrogen gas and I need three of hydrogen gas. That will give me two of ammonia. That's what we're saying. I hope that makes perfect sense. Great. So based on what we learned about the pancake mix and stuff, we're just transferring the knowledge. So we're saying that the coefficients in the balance equation are used to derive the stoichiometric factors. Now, the stoichiometric factors is just what we were talking about, what we said ratios. So That's the ratios we derived when we're doing the pancake mix and eggs. Those ratios, the fancy word for those ratios or those fractions is the stoichiometric factors. They're just fractions. That's what we just did with the pancake mix and stuff. So those factors helps us to be able to calculate proportions for whatever we're trying to create. Okay, great. So let's try this. Coefficients in the balance equation. So we already said that. So for example, to find the stoichiometric factor for NH3 against H. So NH, if you don't know what NH3, NH3 is ammonia. So this is ammonia. I'm trying to write ammonia. Ammonia. Great. I know my handwriting was not that good. So for example, so if we wanted to write the stoichiometric factor, I'm going to be calling it the ratio because I don't want to confuse you. It's the same thing. If I wanted to write the ratio of so here we already have the ratio for ammonia against hydrogen. All they did was that they took ammonia is 2. We have 2 NH3, as you can see, 2 NH3 against hydrogen, and we have 3 hydrogen. So that's the so from here the ratio is what? 2/3. That's the ratio here. Okay, let's write the same thing, but this time we are writing the ratio for nitrogen against ammonia. Everybody, let's try this. I'm going to write that one in red. Nitrogen against ammonia. You're going to take your notebook. Everybody, take your notebook. Nitrogen against ammonia. Nitrogen against ammonia. Let's write it together. So, why is nitrogen? This is nitrogen. Why is ammonia? This is ammonia. So, let's try it. Write it together. Remember, the one you want first, you write it first. I said nitrogen against ammonium. So I want the so whichever one you want first, you write first. So we are looking at nitrogen against ammonia. So nitrogen is 1. So 1 N2 against ammonia is 2 NH3. So for the stoichiometric factor of nitrogen against ammonia, I'm going to have 1/2. Okay. Remember, if I wanted ammonia against nitrogen, then it's just going to be the inverse form. If I said ammonia against nitrogen, I would have had 2 NH3 rather than over 1 nitrogen. Okay. So be careful of that so that you don't confuse yourself. See, now it's instead of 1/2, it's 2/1 because I changed the order. I said initially I said nitrogen against ammonia, and that was 1/2. Now I just changed it and made it ammonia against nitrogen, and now it's 2/1. Okay, so don't forget the order in which you put it can change the ratios, and that's very important because it affects your calculations. Okay, it affects your calculations. Great. So look at this carefully. Any questions? Any questions? Any questions? Great. Any question? Any question? And please, once again, I'm reminding you, you can pause the video at any time, go back again. Okay, so let's move on. Let's move on. Great. So we want to move on. All we've been talking about, we're gonna apply. Now, the last thing I want you to touch on is this. Look at this. So you see, your ratios, the stoichiometric factors, or the ratios in which you write these, they help you a lot. You see, now the ratios can be written, and you can make the ratios anything you want them to be. You see, is here they are describing the ratios as molecules, right? But look at the quantity description. Here it's 2 dozens. Here it's 2 moles. Okay, so we're going to see how that plays into what we are learning. We're going to see it very soon. Okay, we're going to see how that ties into what we are learning right now. Great. So let's go further. I want you to take some time and read this carefully. I'm giving everybody 2 minutes. Read what you see on the screen carefully because we're going to go through this together. Read this carefully. Okay, great. So hopefully you've read this carefully because we're gonna look at this. Okay. So let's go into this together. So this question is now you're going further. All we've been learning, we're taking it a step further. We're trying to understand all we've been learning, but we're taking it a step further. So let's see. Moles of reactants required in a reaction. So we're talking about moles of reactants required in a reaction. Moles of reactants required in a reaction. So all we've been learning now, we're going to take it one step further. Okay. Okay, great. So we want to find the number of moles of reactants required in a particular reaction. How do we do that? Remember all we've been talking about. We're just going to transfer the knowledge we've been learning, all the things we've been learning. We're going to use it here. So I want to know the number of moles of a particular reactant that will be needed to achieve a certain product in a reaction. So let's read. How many moles of I2? I told you to read this carefully, but now I'm expecting you read this. So my first question, what is I2 here? Who knows what that is? I2 stands for iodine. That's important. I2 stands for iodine. Okay. Now we say that how many moles of iodine is required to react with two to react with 0.429 moles of aluminium. Al stands for aluminium. I expect that by now you know what aluminium is. In the following, according to the following equation. So we are going to, this is our, remember, this is our recipe. That's going to guide us. Everything we do is going to be guided by this particular reaction we have here. Okay? Everything we do is going to be guided by this particular reaction we have here. The question is we want to find moles, we want to find moles of I2, which is iodine. That's the question, okay? Moles of iodine. So I want to ask you, what do you think we're going to do first? Based on all we've learned, what do we need to find first to help us find the moles? Remember, our recipe is what? Is the reaction here. Now think about what we did with the pancakes. It's supposed to give you a clue. Think about what we did with the pancakes. What did we do first? It's the same thing. So think about I2 as the eggs in the pancake because look at where I2 is. I2 is one of the reactants. I2 is one of the reactants, right? So it's just like finding a number of eggs and finding the number of eggs you're going to need to make maybe a particular number of pancakes. That's what we're trying to do right now. So think about I2 as the one of, let's say, the egg or maybe the milk. What's the first thing we need to do? What's the first thing we need to do? Anybody? I want you to think about it. Think about it. Think about it. Anyone who? What do you think? Think about it first, okay? Okay. I'm expecting by now you started. So the first thing we want to do is we want to always, using the recipe, which is the main or the original reaction, find our stoichiometric factors or the ratios. It's important. So what are we looking for? We want the most of iodine. So we want to find a ratio that has iodine in there. Okay, so let's start. to help us find, let's here we're going to find the ratio or the stoichiometric. Let me write stoichiometric factors SF. So what's the SF for iodine? We want a stoichiometric factor that has I2, which is iodine in there. So how do we do that? Look at your recipes, your reaction. Look at your recipe here. So there's 3 of I2. So let's see, 3 of iodine. 3 of iodine is needed to give us the product here. What is the product? The final product is 2 of aluminium iodide. Okay. So the question is asking you that how many of iodine will be needed if you have 0.429 moles of aluminium ready, right? So how many of iodine it will be needed to react with 0.429 moles of aluminium according to this reaction? Okay, to produce this product, that's what you're looking for. Okay, so they have already figured out that this amount of aluminium is needed inside to make this, but we don't know the amount of iodine is needed to achieve this, so we want to find that. Okay, so from here we can tell that our ratio is what? Our ratio is what? Our ratio is 3 is to 2, right? 3 is to 2. This is for iodine against the product aluminum iodide. Do you see that? So that's very important for us in this particular question. That's very important for us. Great. Now this is for aluminum and this is for iodine and the final product. So this is 3 over 2. Now let's think about it this way. The question is giving us the amount of aluminium, the mole for aluminium. So this is one stoichiometric factor. We can write another stoichiometric factor where we are comparing aluminium against iodine, because in this question we are looking for the amount or the moles of iodine required to react with the moles of aluminium. So now let's write another one. So this one was comparing iodine with the product. Now let's compare iodine with aluminium. So let's try that. We're going to have, how much iodine do you have in the reaction? There's 3 of iodine again against 2 of aluminium. So that's what we needed. 2 of aluminium. Okay, great. So we have another reaction here. It's still what? 3 over 2. So remember what we said. So this is the stoichiometric reaction. It makes, so now we are going to use this. Now this is what we need, because the question is asking a comparison between iodine and aluminium. So we cannot use this one because this is iodine and aluminium iodide. We want iodine compared with aluminium. So we can use this stoichiometric factor. This is very important. So now let's come here and use that. So we're going to use this. The question already gave us what? 0.429 moles of aluminium. Right? So in our reaction, we know that 3 of iodine 3 proportions of iodine will go with 2 proportions of aluminum. But the question is saying that, okay, what if we have a specific amount of aluminum, which is 0.429 moles? Then how many moles of iodine would you need to react with that aluminum? So let's use that. So we're going to use, our question gave us 0.429 moles for aluminum, right? So you're going to multiply that. The only reason why we are multiplying is because it's aluminum here. Our reaction has aluminum at the bottom, right? 2 of aluminum against 3 of iodine. We are multiplying so that the aluminiums can cancel out, right? That's the only reason why we are multiplying. So now, so you arrange the equation in such a way that the aluminiums can cancel out, and what you're looking for will stand alone. What we need is iodine. So I wanted iodine standard, that's why I arranged it this way, right? So the aluminiums can cancel out. So 0.429. So now let's find our final answer. Get your calculator. If you don't have your calculator, please get your calculator. You need your calculator now. I'm grabbing mine too, so you can grab your calculator too. I hope I have my calculator here. I really hope I do. So let's grab our calculator together and let's solve this. Where is my calculator? If you don't have a calculator at this point, I encourage you to please get a calculator. We need a calculator from time to time. Okay, yeah. So now I have my calculator. So first of all, let's do 3 divided by 2. So if you have your calculator, let's solve this together. So get your calculator. Oh, no, click. 3 divided by 2 multiplied by 0.429. 0.429. And our final answer is what? 0.6435. 0.6435. And that's our final 0.6435 moles. So our answer is that there's going to be 0.35 moles of iodine needed to react with 0.429 moles of aluminum. And that's how we arrive at our final answer. Okay, so we used what they gave us to find what we're looking for. So remember, I started by writing the ratios. I didn't use this ratio because this ratio compares iodine with aluminum iodide. The question did not give us any values for aluminum iodide, so that's why I didn't use that. The question gave us values for aluminum. This is it. This is 0.429 of aluminum. So I needed a ratio that compares iodine with aluminum. So I went for this ratio because it compares iodine here with aluminum here. So that I can get the fraction of 3/2. And based on how it's arranged, I put them here. Okay, so that aluminum cancelled aluminum here. Then we have only iodine remaining. That's what we are looking for. So 3/2 multiplied by the moles gives us the number of moles of iodine needed. Great, I hope this makes sense. This is what we need. This is the first part of this. You need to look at this carefully, make sure you understand this. Then you can apply this because we're going to use it. So pick a time, look at this carefully. I hope this makes sense. So great. Hopefully this makes sense. If it doesn't, just pause, go back again. One last thing I want to highlight. Let's look here. So you realize what is happening here. We had, look at these diagrams. We had aluminium. We reacted aluminium with iodine, and look at what happens. We create aluminium iodide. So the result is, look at what is happening here. We created a reaction, but the reaction comes with other byproducts or other things. Okay, so the reaction vaporizes some of the solid iodine, and the vaporization of the solid iodine results in what you see. There's a purple vapor, whatever this thing is. So you see, we created a reaction. The desired result was aluminum iodide. That's what we wanted to see, and we see it happen here. But it comes with a vaporization. So you see a vapor come out in a certain color. Okay, so keep that in mind. Reactions can be caused. So reactions can be manipulated, if I can use the word manipulated, to create or to give a desired or produce a desired result. Okay, does that make sense? Great, 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 great. So if that makes sense, then let's move on. We want to try. So we're going to. I don't know if I want you to try this on your own, or you want me to try it with you. Which one? So this is what I'm gonna do. I'm gonna make you try this. So a screen is gonna pop up here for you to try this. You're gonna have to try this. Whatever you get, take a picture, submit it, because the screen is gonna pop up asking you to try this and try it yourself. Okay, try it. Let me know what you get. Okay, great. So by now, I'm expecting you to have tried it. You've got your answer. You've you've turned in your answer. We are going to now do this together. Okay. So let's see. So let's see. I'm expecting to have tried this already. So I'm going to now work this. So let's try this. Let's try this. How many moles? I'm expecting you have tried this on your own. I'm going to do this together with you. This is the last thing we're going to do. Then we end for today. How many moles of carbon? If you don't know Ca is carbon. By now you should know carbon. OH is hydroxide. So we have carbon hydroxide. We are looking for the moles. Always remember, what are we looking for? The moles of carbon hydroxide are required to react with 1.36 moles of H3PO4. Okay, so we have PO4. PO4 is phosphate. We have something that has phosphorus and oxygen. So we have phosphate, right? So we're trying to find hydrogen phosphate. That's likely an acid because of the H. Okay. So we're trying to find the moles that I need. So always think about what you need or what they're asking you to find against what they gave you. Okay. So they're telling us to find the moles for carbon hydroxide, but they give us in a certain specific number of moles if we were having this number of moles of hydrogen phosphate. So they're saying that if you have 1.36 moles of this, how many of carbon dioxide would you need to react with this guy according to this equation? So remember, so we need what moles? We need moles of CaOH2. We don't know that, but they gave us moles of H3PO4. They said that is equal to what? 1.36 mole. So first thing we want to find our stoichiometric factors or the ratios from the reaction. So we want a ratio that has this and that in there so that we can use the ratios to help us find the moles of CaOH. So look at your reaction. So let's find the stoichiometric factor we need. This time we're going to go straight to the one we need. We don't want to write the ones we don't need. We're going to the one we need straight away. Okay. So let's look at this. We need once again we need to compare CaOH with H3PO4. So I'm going to have three. Remember, this is what they gave to us. They gave us H3PO4 the most. So I'm going to compare. My fraction is going to be 3CaOH from the equation 2 calcium hydroxide. Sorry. 3 of it is against 2 of H3PO4. That's what we have here. Do you see that? Which is what? 3 over 2. So that's actually the reaction. So to help us find our final answer, we are going to have to multiply our 1.36 mole, which is for H3PO4. Let's multiply that by the fraction or the stoichiometric factor, however you want it. It's 3 CaOH, sorry, CaOH2 over what? 2H3PO4. Remember, we brought this here so that this can cancel this. So now we have we have the 3 over 2. So now put all this in the fraction and let's solve it. So we're going to have 3 over 2. It's just like the first one we did. But this time we're just going to change it now. So we still have 3 over 2. So put this in your calculator. 3 over 2 multiplied by 1.36. And your final answer should be something like this. 2.04 mole. Remember, what we need is mole of what? CaOH2. And this is our final answer. Okay. So that's our final answer. So the number of moles needed is what? 2.04 moles of carbon hydroxide. So 2.04 moles of carbon hydroxide will be needed if we want to react 1.36 of hydrogen phosphate H3PO4. Okay, according to the reaction or according to the recipe that was given. So this is the answer I'm expecting for. If you didn't get this answer, now I want you to go through what I just did and now do your work again. This time do it as it's supposed to be, the correct way, and submit it to me. If you, so I'm going to allow the pop-up to appear twice. Okay. If you got it right the first time, just take the picture of the same thing and just submit it for me. Okay. I don't know if does that make sense. So remember, I asked you to try it on your own and submit it. So you tried it, you submitted. When you submit it and you had it wrong, whatever you had wrong, now you can see the correct one. So correct yourself and submit. So if the first time you had it right, you're good. But just submit the same thing you did the first time, just submit it to me for the second time, okay? Then we are good. Okay, so this will be the last thing we do for today. Okay, we're gonna continue on Thursday, but hopefully you get to practice more. You get to practice more on Wednesday. I'm gonna try and give you more questions to help you practice more on this. Okay, great. Thank you so much for your time, and I'll see you.